So how is everyone today? All right, so then, so today's what, the 25th? So I wanted to give a brief hint or like or just discussion about the Guess the Natural game. So many of you have sort of figured it out one way or another, but I want to sort of explain something to you about the way code is shaped. So like when you've written enough programs and you've sort of thought about it abstractly, you can kind of like start to notice that it has to take a certain shape. So when you have a sequence of operations, that all occur one after the other and they're all definitely going to occur, then you can imagine that like here's some operation and here's another operation and here's another operation and here's another operation. So you're going to do like 4 things all in a row, and they're going to occur in order. And so what it kind of means is that that there's this this shape that's all like in a line. Like first that thing, and then once you've done that, then you're going to do that thing, and once you've done that thing, you're going to do that thing, etc. So that would be like that could be something like you wrote code that says something like, well, x is 1, and then y is 4. Y is 4x. So this could be like x is 1. Okay, first thing, assign the value 1 to x, and then once you've done that, assign the value of y 4x. But you can't assign the value of y 4x until you know what x is, right? So this thing must come before that thing. But sometimes it's the case. That there's a lot of operations, but maybe you don't want to do all of them. Maybe you just want to like pick and choose among the possibilities. And in code, the way that you say that is if, right? So so if you're writing a program that sort of depends on whether or not the input is even, because we've done that a lot, right? So if you're writing a program like that, then maybe you do some things like first we'll do these things. First we'll do these things, and then we're either going to do that one, or we're going to do. I'll shape this one like a square just so they look different. So we're either going to do that one, shape it like a star, I guess, or we're going to do a square, but we're not going to do both, right? So that's going to depend on something. So here, we're either going to do that one, or we're going to do that one. Okay, so the branchiness in the shape represents an if. That's what that is. So then you could go on from there and say and then I'm going to the last thing I'm going to do is that. So a code shaped like that would be like that would be representative of an if being there. Which is to say that can you make it from the beginning to the end without passing through star? Yeah. Can you make it from the beginning to the end without passing through square? Yeah. It just depends on whatever occurred right there. So in the Guess the Natural game, when you ask the oracle a question, the oracle can respond in one of 3 ways. And what are those 3 ways? Right, they can either say that you guessed too low, you guessed correctly, or you guessed too high. So as a result, in the oracle game, in the down part of the oracle game, okay, when you're asking them stuff. So this is in the down part of the Guess the Natural. So when you're doing that, there's some stuff you got to do at the beginning, I don't know how many things you got to do at the beginning, but this first sequence of things that you're doing, that might represent like you're checking to make sure that the arguments make sense. right? So that someone didn't like, someone didn't make the lower bound a banana, you know, or whatever. Like, no, we're not gonna play. If you tell me you're thinking of a number between banana and 8, I'm not gonna play. But suppose you get past that point, then you know, if the oracle can respond in 3 ways, and if I name this this one question mark, the place where you're asking the oracle a question. So if that's the place where you ask the oracle a question, then you know, once you get there, you have to branch. You have to say, well, if the oracle did this, then I do that, etc. So there won't be 2. How many will there be? There'll be 3, right? Because that corresponds to the 3 ways the oracle could respond. So it might, you know, you know, could conceivably write code that looks like this, and those correspond to the 3 different ways the oracle could respond, right? Too low, correct, or too high. So, and you're going to do 3 different things, right? So then, if the oracle said too low, you do one thing. If the oracle said correct, you do one thing. If the oracle said too high, you do a different thing. Okay. So then, you know, eventually the function exits. So I'll just put a point over here, which just represents I'm leaving. So now, if your code is shaped like this, is it, presently, is it possible to get from the beginning to the end without asking the oracle a question? I mean, do you observe that if you start here and end there, every path goes through question mark? All of them do. You can't make it from the beginning to the end without passing through there. So if your code is shaped like this, then you are unconditionally asking the oracle a question every time. Every time. So here's the deal, right? On this, the rule is that not only do you have to find the hidden number. So you can write code that is shaped in this way that does find the hidden number. It finds it correctly. But another aspect of the rule, another aspect of the game is you have to ask the minimum number of questions. Okay, so then you can have code that's shaped like this that determines the correct answer, but in fact asks too many questions. Because under what circumstance do you not need to ask any more questions? One of them is this one, where you asked the oracle and they said, you got it. But there's actually another circumstance. Under what circumstance do you not need to ask a question? Sorry? Well, even, I mean, there's different ways to codify it, but I'll say it as simply as possible. I'll say it like this. If the oracle says, you know, I'm thinking of a number between 2370 and 2370, then, you know, how many times do you have to ask the oracle a question? None, right? Because you know, because there's only one possibility. There's no need to ask any more questions. So if you keep getting an error that is more or less saying something like, you know, you were expected to ask, you know, 23 questions, but you asked 24, that's because your code is shaped like this. That's because when the oracle says, I'm thinking of a number between 23 and 23, you're saying, okay, I'll calculate the floor of the average, which is 23, and then ask, what do you think about 23? And the oracle says, yeah, that's it. So rather than that, to be correct, you know, before you ask the oracle a question, you need to ask yourself, do I even need to ask a question? So what I'm saying is that you know, you're gonna have to do some things in the beginning, right? Make sure that you know, no one called your function with like you know, like an avocado or whatever. They've got to be legitimate arguments, and then you have to ask yourself, do I even need to ask a question? Because the answer might be no. So the question is then, you know, do I need to ask a question? Maybe yes, maybe no. Right? And then if that one is no, I don't need to ask a question, then, you know, you can just jump to the end somehow, whatever that means. But if the answer is yes, in fact I am going to need to ask a question. Now you ask the question. You say, okay, I asked the question of the oracle, and then you know, there's 3 possibilities. of how the oracle can respond. And then you're going to leave. So leaving, I'll just represent as that dot right there. And so now, concerning this, is it possible to travel from the beginning to the end without going through the question mark? It is. So now the branchiness in these drawings, that represents an if. That's what that is. So so notice that there's two branchy things in this one. That means that there must be two ifs, right? But it's not an if, and then a little bit later you do an if. It's not like that. Rather, notice that the branchiness happens here, and then even more branchiness happens. So that means that it's not an if, and then you're done with that if, and then a little bit later you do another if. Rather, what is it? Yeah, it's an if that is inside of another if. You know, like those Russian dolls that are shaped like eggs, and then you give them to a little kid. You know, you hand it to them, and you're like, hey, take a look in there. And they open it up, and then there's another one inside, and they're like, oh! It's so funny to watch them see that for the first time. And then they, you know, frantically try to make it to the bottom. So, you know, it's like that. So if there was a if and then another if a little later, the code shape would you know, look like this. You know, so maybe there's an if, and there's two alternatives, and then in either case, you get back on the main line, and then a little bit later, you do another if that has, you know, maybe like three alternatives. And then get back on the main line. So there's two ifs in this. There's two branch points. But you do this branchiness and then get back to doing the normal stuff, and then you branch a little later. So does everybody see it? So in the end, what I want you to see is that in this case, if the code is shaped like this, it's possible to make it from the beginning to the end without asking a question. So in all of the exercises, I have some reason, right? All the exercises I give you, I have a reason that I'm asking the question. Some of them are sort of obvious, like, you know, I say, hey, let's play a game. You know, so then in some sense, the guess the natural assignment is so that you can figure out how to do that. But the other point of the assignment is to force the hidden part that I don't really say, at least at the beginning. The hidden part that I'm not telling you is that I've constructed the assignment so that it's impossible to solve it without doing this. The only way to solve it is to have an if inside of another if. Any question about that? Good. Good. So then now that being the case, last time we were talking about GCD. So to summarize some things about that. To summarize some things, we talked about Euclidean division. So, you know, on the one hand, we have Euclidean division. And that's saying that if we say let n and d be in the naturals, with d a positive natural. So I'm saying give me any natural n and any positive natural d. Then there exists unique q and r that are in the naturals, such that in fact two things, n is equal to q d plus r. So being interpreted, q is called the quotient and r the remainder. So q and r must satisfy that equation, but in addition to that, r must satisfy an inequality. What inequality? So it's going to be r is in between two things. So like, you know, if we were playing the bucket of M&Ms game, and I said, you know, we're gonna pass the bucket along, and you're gonna take out 5 M&Ms, if it's possible to do so, and if it is possible to do so, then do that and hand it to the next person. Then when the game is over, what must be true about the number of M&Ms in the bucket? It's got to be less than 5. Otherwise, y'all wouldn't have been following the rules, right? So R is how many M&Ms are left in the bucket, and how many are we taking away from the bucket? D. So what must be true about R? Less than D. So R is less than D, and then in most sources, books, and what have you, this is included. So R is between 0 and D. Strictly speaking, the way that I've written things, I don't have to write the 0. Why not? Yeah, because I said R is a natural. But you know, for our definitions in this class, when we're talking about Euclidean division, it's occurring only over the naturals. But I do want to let you know that it is possible to define the same thing over the integers, where things can be negative. But we're just not talking about that in our class. That's just, you know, I have to make the cuts somewhere, and if we only talk about the naturals, it makes our lives a little simpler. Okay, fine. So that's Euclidean division. Now, one thing that we've said sort of implicitly is that if you what am I trying to say? So if you Euclidean divide n by d, so if you do that, and you obtain a q and an r, so if you do that, as above, then you know, to give an example, I could say, well, Euclidean divide 24 by 3. So what's the quotient? How many groups can you make? 8. And how many are left over when you've done that? 0, right? So in that special case, you know, what we say is that, you know, 3 is a proper divisor of 24, because there's nothing left over when you do it. Another way to say that is that 3 is a factor of 24. So if R is 0, R is 0, then you know you have the following consequences. So in language you say that D is a proper divisor of n. Or instead of saying a proper divisor, you could say D is a factor. Those are synonyms. Factor is a little better, in my opinion, because you know, of these 4 things that are in there, that one is called the dividend, the thing that is being divided. So in grammar, you know, subject, verb, and object. This is the object, the thing that the action is occurring to. D is the divisor, is the thing doing the action, so it's the subject in the sentence. So dividend, divisor, and you know, but those aspects of language are sort of lost these days in English. So I think making even one more phrase that has a word like div in it is not good. So I like to call it factor. Fine. So what you write then in this case is that D is a divisor of n. So that's how we write it in our class, that vertical bar going through a less than. Now, you know, again, to make sure that you can read other source material, do understand that in other source material it's very often written that way, without you know, it's just written that way without the less than. But the reason why I don't like that notation is because you know, this is a true statement, but sometimes you want the 23 and the 70 to be in opposite positions. You know, you want them to be like this, and you still want to have the less than relation. So you can write it this way, so it works. It works because that symbol can be turned around. Okay, but if you use that, then this is true. That's a true statement. But if you wanted to have a true statement, and the 24 was on this side, and the 3 was on that side, then you can't do it, right? Because that bar is horizontally symmetric. You know, you can't flip the bar around. See what I mean? But you can. You know, if you make the symbol anti-symmetric, then you can. You can say, well, this is true, and that is true. Okay. So we have that, and then this thing, it does define an order. And now we've been talking about greatest common divisor, and the thing is that a lot of y'all have probably every one of you has seen greatest common divisor before, like in 7th grade or whatever, and some of y'all have programming experience, and if you have programming experience before, took some class or whatever, then it's very likely that you wrote a greatest common divisor function before. And if that's the case, then you're sort of then there's possible that you're in a real bad group where you've been really misled about what greatest means. So we have 2 orders that we talk about on the naturals: the linear order, but we also have the division order. And the thing is that the word greatest in greatest common divisor is not referring to the linear order. That's not what it's referring to. It's rather it's referring to the division order. And that makes funny things, because what is the least natural concerning the linear order? It's 0. And what is the least natural concerning the division order? 1. Because 1 divides everything. So 1 can always be written on the left of everything. So 1's the least. What's the greatest natural in the linear order? There isn't one, right? There isn't a greatest natural in the linear order. What's the greatest natural in the division order? 0. Because everything divides 0. And if that's disturbing to you, then okay, we'll go through an exercise. Okay, so I just put 0 M&Ms in front of you. And now I'd like for you to make groups of size 2,370. So go ahead and do that. Okay, so now that you've made all of the groups of size 2,370, how many are left over? 0 are left over? Ha! What does that mean about 2370? That means it's a factor of 0. It's a proper divisor. Because when we did that, there was nothing left over, right? That's what it means. So 0 is the biggest. Okay, fine. So we've got this concept of greatest common divisor. Fine. So Euclidean blah. So it seems like I'm missing something that I want to add. Euclidean division. Now we're fine. Okay, so then, in order to calculate greatest common divisor, right? The way that we want to calculate it is that, we first talked about this thing called Infimum, because I was trying to prime you for this idea. So Infimum. So, I could ask a question like, concerning the linear order, and concerning sets, and concerning the open set from 0 to 1, what is the minimum? There isn't one. So this does not exist. It doesn't exist because the definition of the minimum of a set X requires the element to be in that set X. So there is no minimum for this for the reasons that we've already discussed. But nevertheless, I think it's clear that somehow we want to be able to say something that when I ask about this set, I mean something that is like minimum, and I mean 0. Does So it can't. The thing that we're talking about can't be called minimum because that ain't going to work. But you know, you want to be able to pick out 0. So the name of that thing is called the infimum. And the way it works is you define what a lower bound is. So like in the linear order, and concerning the open set 0 to 1, -5 is the lower bound, because -5 is less or equal to everything in there. And -55 is a lower bound. -55 million is a lower bound. -0.55 is a lower bound. I don't know why I'm saying 55, but so there's lots of lower bounds for this set. So I could say, well, the lower bound, when reckoning using the linear order, the set of all lower bounds of this set is what? So what is the set of all lower bounds of that set? Right, it's -infinity to 0, which is to say, these are all the numbers that are less or equal to all those numbers. Okay, now have a look at that set. Now that set has a maximum, doesn't it? What's the maximum of that set? It's 0. It's 0. So here we have it. Is that the definition of infimum of a set? Well, I'll say specifically of this set. So the infimum of that set is, in fact, it's the maximum over the linear order of the set of all, of the set of all lower bounds of that set, where the lower bounds are reckoned in the linear order. So I'm asking about, you know, what's the maximum of this set? And the answer is 0. So here's what I want you to understand. The set of all lower bounds, sort of conceptually, is like it's saying something like, tell me all the things that are little compared to this, to that one. You know, what are the little things compared to that? And you say, now I've got the set of all the little things. Well, the infimum is the biggest little thing. That's what it is. You say, oh, I found all the little things, and that's the biggest one. So you know, we could turn it around and instead of saying the biggest little thing, we could say the littlest big thing. Okay, and then instead of being infimum, that's called what? Supremum. Okay, but this idea of being able to order stuff and finding the collection of all small things and then finding the biggest one in that collection, this idea is pervasive in math. When you're talking about the reals, it happens to be called infimum. But when you take the naturals and you consider the instead of the linear order, if you consider the division order, what's the name of the if you have two numbers and you consider the set of all lower bounds of these two numbers and then you find the biggest one? So the biggest little thing with regard to these two numbers, what's the name of that? That's greatest common divisor. That's what that is. So GCD, defined on the naturals. So we have got a function, GCD, of A and B. What it is it's the maximum. You know, I'm writing less or equal there to remind you that by maximum, when I'm talking about maximum, I'm talking about the linear order. But here, I'm not talking about the linear order, rather I'm talking about the division order. So the maximum with regard to division order of the set of all lower bounds with regard to division order of the set containing A and B. So that's GCD. We won't have time to talk about it today, but we are going to talk about it next time. So instead of finding the biggest little thing, which is GCD, among the things that we talk about next time is going to be we're going to find the littlest big thing. You know, whatever that is. I don't know. Understand, okay, that GCD of two numbers is the biggest little thing of that set. But also understand that there's nothing magical about having two elements in a set. So what I want you to see is that this definition just as well defines the GCD of three numbers. So instead, you just take these three numbers and find the set of lower bounds and then find the biggest one. So you can find the GCD of 3 numbers, 10 numbers, whatever you want. Okay. So now that's neat and everything, but that doesn't really tell you how to calculate. It just gives you a definition. So now we want to be able to calculate. So here we go. This is what we said last time concerning GCD of So concerning GCD of A and B. Here's some facts that we were able to discover just from the definition. And so in the first place, is this true? Is it the case that the GCD of A and B is the GCD of B and A? So can you commute those things? Yeah, you can do that. You can do that in the end because it's just a question of, well, the set containing A and B, is that the same as the set containing B and A? Yeah, because the order doesn't matter. Okay, so that's true. So if it ever came to pass that we were calculating that one, and for some reason we preferred that one, well, then we could do that one. Similarly, how about the GCD of 0 and B? Which is to say that, what if it comes to pass that that first argument is 0 and then, that other one is whatever? Then what's the answer? Again, so to give you an example, how about GCD of 0 and 24? Well, let's consider for a moment the divisors of 24. So they always come in pairs. So 1 and 24, 2 and 12, 3 and 8, 4 and 6, and these are all of them. And of those, in the division order, which one is greatest? So what is the greatest divisor of just 24? 24. Okay. Now, what is the set of all divisors of 0? All of them, right? Everything divides 0. And if 24 is the biggest one concerning 24, and this one has all of them, so what's the biggest one for them both? 24. 24 is the biggest one that does both. So the answer, in this case is 24. So what's the answer here? B, right? So if it ever comes to pass that we are calculating GCD and the first one is 0, then the answer is the second one. Okay? Finally, these two are not enough to be able to calculate. But this next thing will give us something that is enough. And it is the following. We can say, all right, suppose that D is the GCD of A and B. Suppose that for some reason we know that. Like maybe we went ahead and wrote out the whole division lattice and we actually just did it. Suppose that we know that. By definition, we can say, therefore, there exists little m and n in the naturals, such that A is MD and B is ND. That's what it means, since if D is the greatest common divisor, then it is a divisor. So A can be divided properly by D, and B can be divided properly by D. And so I'll say, without loss of generality, I'll say that A is less or equal to B. So what I mean is that in the linear order, A is the little one and B is the big one. I can say without loss of generality because even if that wasn't true, then I could just say, well, I can just swap them according to that. And then it would be true. So, all right. So the reason why I want that is that as a consequence of that, I can say, therefore, B minus A is greater than or equal to 0. So I need it to be greater than or equal to 0. And therefore, B minus A is a natural number. So if I subtracted them in the wrong order, then I might get a negative number, and then I'd be out in the woods. That wouldn't work. Okay, so then now just algebraically, algebraically, I can say, therefore, B minus A is, according to that, is ND minus MD, because after all, that's what we said. Then D is a common factor, so this is, in fact, N minus M D. Right? So then if D divides A and B, then it also divides their difference. So, we can say that, D is a divisor of B minus A. So we found yet another number. So D is a divisor of A, and it is a divisor of B, and furthermore, it's a divisor of their difference. But, so that's that, and notice, so and, okay, concerning this, is this true? So is that true? It is, right? It's got to be true, because if you have B things and you take away A of them, then that's less or equal to B, because A was a positive number. So if you had 8 things and you took away 3, then that's less than 8. So that means that this one is smaller. This one is smaller. And because this one is smaller, and because that number is the greatest divisor of A and it's the greatest divisor of B, and that number is smaller than, less or equal than both of them, then that means that, in fact, D must be the greatest divisor of that. Okay? So that's a little bit of hand-waviness. There's something to say there, but I'm avoiding it because I'm in a hurry. So therefore we can say, so as a result, we have this thing that we wrote last time. We have a function. The greatest common divisor of A and B now can be calculated. We now have enough to do it. So, all right, here's the deal, is that we're going to arrange matters to make our life simple. We're going to make it to where this is the little one, little, and that's the big one. And this is going to be reckoned in the linear order, which is just to say we want to make our life simple by being able to count on that. Now, what if someone is messing around, and instead of asking for G of like 10 and 20, what if they ask for G of 20 and 10, so that the arguments aren't in the order that we like? We'll just switch them, right? We'll say, okay, so if you're messing around with me and you give me you give them to me like that, then I'm immediately just going to put them the other way. So swap them. All right? Then how do we know when we can stop? How do we know when we don't have to go any further? Now that case, right? So if we get beyond clause 1, we know that they're in the order that we like. So if it's the case that the little one is 0, if the little one is 0, then what's the answer? The big one, right? Okay, and then finally, if they're in the right order and the little one isn't 0, then that means that we're not able to make a conclusion, but at least we can make some progress. And the progress that we can make is, according to 3 there, is that the GCD of A and B is the GCD of A and B minus A. And the reason why that's progress is because B minus A is definitely less than B. It's definitely less than B because if that was, if that's not true, then A is positive, right? So A had to be at least 1. So we made that the second argument at least 1 smaller. So that means we're descending. So we make progress. So it's possible to calculate. So that being said, now we're going to have a quiz. Okay, so then you can use your notes. It doesn't matter. It's only going to take 5 minutes. It's very simple, and then we're going to continue. please be sure to bubble your net ID. That's the thing you log into Blackboard with. Not your student ID, not the thing that starts with a number. Okay, so it's just a completion quiz. So we're going to go over the answers real quick, and then I'm going to collect them. You know, of course, that's the function that I just wrote in the notes, right? It's exactly the same thing. So to evaluate g at 23 and 0, you know, so what do you have to do? according to the according to the rules. Now you got to swap them, right? Someone, who did that? Who gave it to me like that? So okay, now they're in the order that we like. And then then we realize, hey, the little one is 0, so that means that we're done. So the answer is 23. Okay, for the next one, all that this one is just like the first one, it's just one removed from that, right? So they're in the right order, because remember, little means less or equal. So they're in a fine order. So we have to end up, we haven't figured out the answer yet, so we make some progress. So we take a bite out of it and say, we'll take 70 away from that, and now we have 70. And then we realize, oh, look, they're in the wrong order. And then okay, now they're in the right order. And then you realize, hey, the little one is 0. Okay, so then that's the answer. So what's this one? And why this one? Right. So are they in the right order? Yeah. Is the little one 0? Yeah. So the answer is 0. Now I write this one down. I always carefully write this one down, because here's the deal: is that if you have any prior programming experience, like you've actually written a few programs, and maybe once upon a time you wrote a GCD thingy, and then you read somewhere about like because of psychological conditioning that you can't divide by 0 and and all this stuff, and then you have so many zeros there, and it says divisor, greatest common divisor, that mixture of stuff causes students to panic. And I find that if a student has programming experience before they get here, and also they know that you can't divide by 0, and also they wrote a greatest common divisor program before they got here, then this one really sticks. They just can't fathom that this could be right. But it is right. And if you're still having difficulty accepting that, it is only because you're still thinking that we're talking about the linear order. We're not. We're talking about the division order. Okay, and this one's just sort of like normal, right? So then, are they in the right order? Yes, so take a bite. Are they in the right order? Yes, so take a bite. They're not in the right order. Put them in the right order. Okay, take a bite. Are they in the right order? Yeah, take a bite. Are they in the right order? Yes, take a bite. They're not in the right order. Okay, put them in the right order. Oh, look, the little one is 0. That's the answer. Okay, now this is a terrible way to calculate GCD. This is not even close to a good way to do it. But it is a way. Okay, it works. So now I'm going to collect them. So would you please pass them to the right? All right. So what we're saying from the previous page, we're saying so basically here's the identity that we're talking about. The GCD of A and B is the GCD of A and B minus A. And that's the case as long as B minus A continues to be a natural. All I mean is that you make that subtraction, and according to the way that we define things, we only talk about naturals. So if this is negative, then that's not going to work. So what we're saying is that you can take away an A. Okay, so 1A. But if it works for 1A, right? If it's just one of them, then just ignoring that and just saying that's whatever it is, then I should be able to take an A from that one too, right? So this should be equal to GCD of A and B minus A, right? As long as that continues to be a natural, right? We can't. If that's negative, then we can't do it. But don't we have a better way to say b minus a minus a? Ah, that's better. Right, so GCD of a and b minus twice a. But if it works for twice a, then surely it should work with 3 times a. Right, and this again is going to work as long as b minus 3a is natural. So if b minus 3a has become negative, then we can't do it. So if it works for 3a, maybe it'll work for 4a, and if 4a, maybe 5a, right? So what I'm saying is that as long as we keep that second argument natural, then this should be equal to GCD of any of these, right? So b minus even a QA, where Q is just says how many times we've taken A. Well, here's the deal. If I say that X is this set, so X is the set of B minus a single A, B minus 2 A's, B minus 3 A's, dot dot dot, and then B minus Q. Q just represents how many A's we've done, and then dot dot dot. It continues. Then because this is assuming that A is positive. Because if A wasn't positive, then we wouldn't have any work to do. If A was 0, the answer is B. So what I'm telling you is that that number is different than that number is different than that number is different than that number. Those are all different. And this is a decreasing sequence. So that's the biggest one, smaller, smaller, smaller. So this set right here, in fact, is not a subset of the naturals. Rather, it's a subset of the integers. All that is to say is that eventually we're going to get to negative numbers. So if I define y is equal to that set x, but I only want the ones that are natural. So if I say that y is that set, then is there anything at all in y? Does y have anything in it? Yeah. What's definitely in it? B. And if we have that, and we furthermore say that A is less or equal to B, then that means that that one is in there too. So, but at any rate, it's not empty. It's definitely not empty. And so what we're saying is that y is a non-empty subset of the naturals. And by the well-orderedness axiom, we know that there must be at least one. So there's got to be a smallest thing that's in y. So by the well-orderedness principle, there exists a least element. A least element R, which is an element of y. Now, because they all take that form, because it's b minus 0 A's, b minus 1 A, b minus 2 A's, b minus 3 A's, all the way down, that means that we can write R is equal to b minus QA. That's what that means. So where this, for some Q is what I mean to say. Now, here's the deal, is that, we had B, and so we say, okay, we're going to take away A, and then we're going to take away A again, and then we're going to take away A again, and we just keep doing it until it's not possible to take A away anymore. So, in fact, we know something that's, that R must satisfy an inequality. What inequality? What is it? Well, yes. So 0 has to be less or equal to R, right? Because we said that it's got to be in there, so it's got to be natural. So that's a consequence of it being natural. But in fact, we can put something on the other side of it too. What? It's got to be less than A. Because do you understand that this is just an abstract way to say, suppose that I give you a can full of B M&Ms, and I start telling you to take away handfuls of size A, then, you know, you can only do that q times. And then what's left over is that much, and it's got to be less than A. This is Euclidean division. That's what this is. So, so you know, the surprising thing is that that's saying, you know, double surprise there, is that in fact GCD of A and B, in fact, is the GCD of A and R. You know, because all of these are the same. A and R, where R is the remainder of Euclidean division of B by A. But you know, even better, in some sense, is that because we know that R and A satisfy that inequality right there, because they satisfy that inequality, we already know, are those in the right order? They're not, right? Because R is supposed to be small compared to A. So we can do even better and say, actually, it's this. Or it is also this. So if we had some way to do Euclidean division, and maybe even do it fast, we'd be in good shape, right? Ah, it's a good thing that we just did that, right? We did Euclidean division, and even we found out a way to do it quickly, using divisions by 2 and multiplications by 2. So we can calculate R quickly. So as a result, that's telling us. Therefore, we could define a new function. So G was a function that calculates GCD, and now here's a new one, H, which will also calculate GCD. So the G one had 3 clauses. One of them was the swap clause. Are they in the wrong order or not? And the next one was have we reached the end? Has the little one become 0 yet? And the other one was like, okay, let's take 1 byte. Let's take a byte of size A. So let's do this one with those the same 2 first clauses, which is to say that if some joker gave it to us in the wrong order, then okay, all right, we'll put it in the right order. And then if we've reached the end, so how do you tell when you've reached the end? When the little one is 0. So when the little one is 0, what's the answer? The big one, right? When the little one is 0, the answer is the big one. And then now finally we're gonna so if neither one of those, then we have more work to do. In G we were saying let's take a byte of size A. That's what that one was saying. In H, in this one we're saying let's take as many bytes of size A as possible. Let's just as many bytes right now. Let's do it right now. And so the answer is it should be R and A. So this is otherwise. And this is where B is equal to Q multiplied by A plus R is the Euclidean division of B by A. Okay, so notice that we're definitely making progress, because not only is that, consider the 2 arguments, right? So comparing it to G, G makes progress because B minus A is smaller than B, right? But it might not be smaller than A. A is the small one. B minus A is smaller than B, but it might not be smaller than A. But now look at this. R, not only is it smaller than B, it's also smaller than A, right? It's smaller than the previous small one. So what we're saying is that that's the little one, and the new big one is the old little one. So we've gotten like a lot smaller. So this is the usual way that you calculate GCD, if you've ever seen it before. Any question about it? Okay. Now, here's the deal. Anytime you make a division, you calculate a division on a computer, it's expensive. So we defined a quick way to do Euclidean division, and it is quick, but you've got to understand that that's relative. That's quick for a division. But anytime you're doing division, it's sort of, in some sense, necessarily a slow thing. Okay? So then what we want to do is we'd like to be able to calculate GCD in the fastest way possible. We want to calculate GCD in the fastest way possible, and that means that we're going to avoid Euclidean division. So G avoids Euclidean division, but it's super terrible. It's slow, because you're just taking like 1 byte of size A. So it's slow. It's no good. Now, when we did molt in R, remember? We did that, and it was slow. It was slow because if you wanted to do like 100 times x, you've got to do 100 things. You got to make 100 x's and then add them all up. And that's slow. But how do we fix that? Can you remember? Yeah, we said the computer counts in base 2. The computer counts in base 2, and what molt in R is saying is like, let's assume that the computer knows how to add, but maybe it doesn't know how to multiply yet. So when you define the function molt in R, what you're doing is you're defining what multiplication means, but you only use addition. So if you do that, it's kind of slow. But then if we give ourselves permission to use multiply and divide by 2, holding 2 to be special for some reason, then suddenly we can do it much faster. So why do we say that, okay, the machine can add, and also we're going to give ourselves special permission to multiply and divide by 2. So why do we give ourselves that special permission? Yeah, because the computer counts in base 2. So whatever base you're in, multiplying or dividing by the base is shifting the point. Just like if you wanted to multiply by 1,000, you just move the thing over. There's no work. It's very cheap. Same thing with a computer. So here's the deal. Let's calculate GCD, but let's use that trick. Okay? And what we want to do is we want to avoid doing any Euclidean divisions. All right. So here's the deal. Is that concerning, if we want to calculate GCD of A and B, so that's what we want to do. Then concerning those A and B, since they're natural, now detecting if something is even is also very cheap. The reason is because, again, you can tell if something's divisible by 10. In base 10, it's very easy to tell. How do you tell? Yeah, the least significant digit is 0. So how do you tell if something's divisible by 2? In base 2? If its least significant bit is 0. So it's just literally you're just looking at the least significant bit and just asking, is it a 0 or a 1? So it's super cheap. So we could say, all right, concerning A and B. A is it's either even or it's not. Right, those are the only conceivable possibilities. And similarly, concerning B, it's either even or it's not. So what I want you to see is that where our, if we want to be clever concerning powers of 2, divisibility by 2, we have to be able to write something in each one of these boxes. There's 4 possibilities. So let's consider. Suppose that A and B are both even. Say like I'm asking about the GCD of say like 20 and 30. They're both even. So that means that what must be true about the GCD? It has to be even, right? Because if the two numbers are even, the GCD's got to be even, right? So I'm asking a question that is like this. Well, the GCD of 20 and 30 is what I said. Well, suppose we take the 2. Suppose we take a factor of 2 out of 20. So if we divide out a 2 out of the 20, what do we get? We get a 10, right? Whoops. I'm missing something there. And if we divide a 2 out of the 30, what do we have? 15. So now, using your, just mind, the GCD of 20 and 30 is 10, right? And what's the GCD of 10 and 15? 5. So at the cost of dividing both of those by 2, we can calculate just this GCD and do what with it? Multiply it by 2, right? So if they're both even, then we can say that the GCD of AB is in fact twice the GCD of what? Of what? Half A and half B. Right? And that means that both of these are smaller now. Okay, so that one makes progress. What if A is odd and B is even? Then what must be true about the GCD? Can the GCD be even? It can't be, right? So if I ask you about the GCD of an even and an odd number, the GCD can't be even. So in fact, we could say that this one's even easier. The GCD of A and B, if A is odd and B is even, is actually just the GCD of what? Of A, because A is odd, and B over 2. So we can just get rid of that 2, because B didn't need it anyway. It's not part of the GCD. It's gone. Okay, now how about this one? This one is the symmetric case. So what if they're even and odd, but in the other way? So GCD of A and B is what? If A is even and B is odd? Yeah, half A and B. So what we're saying is that the little one is even and the big one is odd. Well, let's just get rid of that 2 in the little one. It wasn't using it anyway. Okay, finally, what if we're down here if they're both odd? Well, we can't do the divide by 2 trick, but we still have the take 1 byte trick, which is to say that this is a GCD of A and B is the GCD of A and B minus A, right? Take 1 byte. So notice that we're able to fill all 4 boxes, so that we have we filled all 4 boxes and we didn't do a Euclidean division anywhere. Okay, so now I'm just going to write down the definition, and then we can be done. So we did G and then H. So now we're on I guess. So here's yet another definition of greatest common divisor. But it does it, in fact, quite quickly, and does not do a Euclidean division. Okay, so if they're in the wrong order, then we put them in the right order. If the little one is 0, the answer is the big one. If they are both even, then what's the answer? Right. If they're both even, then we'll take out that even. We'll take out that 2 from both of them and say that the answer's got to be twice that, whatever that is. Now, if A is even, and remember that for functions, clauses are evaluated top to bottom, okay, with first match wins, which is to say that here this clause says both even. So if this clause says that A is even, that implies something. What does that imply? That B is odd, right? That's what that means. So in this case, so if A is the even one, then A, you don't need that 2 there. So then we'll continue. And then if B is even, now again, that clause, what does that clause mean? B is even, and then what's implied? That A is odd. Okay, so you know, B, if you're even, then and A isn't, then you don't need that 2 there, B. And finally, we can say, okay, well, oops, yeah. You know, if we can't do the parity trick, then we just take a byte. A and B minus A, otherwise. So, now, the last closing statement is this. So when you ask your the computer to calculate GCD, and it's not something that you write, but it's something that, you know, someone clever wrote. That came off really bad. What I mean is that what I mean is someone, you know, took a degree, you know, in electrical engineering, and they built a thing that does it. That's what I mean. Like someone built a machine whose purpose is to do that, and they've really thought about it. This is the way that it's happening. So this is the way that it's actually being done. Now it's slightly different because you can make other cases, like you can say, like instead of exiting when A is 0, you could also exit when A is 1. So like, what's the GCD of 1 and B? It's 1, right? Because if one of them is 1, then the answer is the other one. Okay, so there's slight modifications you can do to this, but more or less this is as good as it gets. Yeah? Yes, thank you. I don't know what happened there. All right, y'all have a nice Thursday.